Well, hello, everybody. This is the fourth installment of the Harvard Sports Analytics Lab and the American Statistical Association section on statistics in sports seminar series. And today we're really delighted to have Lars Hvattum with us to speak today. So Lars received his PhD from Molde University College in Norway, where his research focused on the area of logistics. He went on to do a postdoctoral fellowship and then a professorship at the Norwegian University of Science and Technology before moving back to Molde University College in 2015 to become professor of quantitative logistics. Lars's research focuses on exact and heuristic solution methods for optimization problems arising in logistics, including how to model uncertainty when optimizing decisions and how to solve the resulting optimization problems. However, he also has publications in sports analytics, including results on results prediction and ranking methods for players and teams. And today he will tell us about regression-based player ratings in soccer. And so just before I hand on over to Lars, I'll just say that the way in which we normally manage questions during these seminars is if you have a clarifying question, please raise your hand, by which I mean your virtual hand. And we can call on you. Whereas if you have a substantive question, please save it for the Q&A at the end of the talk. And with that, I'll hand over to Lars and we can get started.
Well, thank you, Laurie. So I'll try to figure out how to share my PowerPoint here, and I hope it's working. So let me start by thanking the organizers for having me on. It's a pleasure for me to give this talk to you today. I'd also like to mention that I have some fine folks listed on the front page here with some collaborators, without which this work would probably not have been done at all. So the main topic is regression-based player ratings in soccer. So let's see. There we go. I guess a little bit about the motivation first. So what we want to do is basically to figure out sort of a ranking or a rating for different individual players in soccer. So I think this is important for several reasons. First of all, because there are decision makers in this sport that kind of rely on being able to evaluate how good a given player is, just for recruitment, contract negotiations, things like that. And this images illustrate kind of the individual awards being handed out in soccer, which is kind of maybe a paradox given the sport is supposed to be a team sport. But as you can see, there's a big tradition for this individual reward handing outs. When trying to evaluate players in an objective way, there's a matter of what kind of data is available. And the type of data that you have will put some restrictions on what kind of player evaluations you can perform. So I like to differentiate between two different types of player ratings. One group of them being so-called bottom-up ratings, where you observe the individual players and the actions that they make during a game. In soccer, that would be things like goals scored, saves made, dribbles, passes, and so on. Also sprints and tackles and bookings. And then, for example, by assigning different values to the different actions, you can maybe derive a formula for the overall contribution of a player. And the other type of player ratings, which is the type that I will talk about today, I like to call top-down ratings. And the idea here is that you don't observe what the individual players are actually doing. What you observe is how the team performs as a whole. And if you do that over a long time span, perhaps it's possible to isolate the contribution of different players based on whether or not they were active in a given game, and then distribute credit for the performance of the team onto the players, simply based on their presence or absence. So the type of data that we have at hand when we try to do this is typically what is known as match sheet data. So I picked just a random example here, as you can see. But the idea is that you will have the lineups for a given game, which players starts the game, which players are on the substitute bench and which substitutions are made and at what time during the game. When are the goals scored, and are there given out any red cards that will make players leave the pitch? So using this kind of data, is it possible to say anything about sort of the relative quality of the different players involved? I'll start with a little history lesson, I guess. So if we go back to the 1950s, that's where the concept of plus-minus ratings arose, and plus-minus ratings is what I'm going to talk about today. So that was an early attempt of evaluating individual players, and there was a coach at the Montreal Canadiens who sort of figured out this way of doing it. Plus-minus ratings and in this basic form is essentially that from the perspective of a player, you add up the goals scored by the player's team, and you subtract the goals scored by the opposing team. Then you get a difference, a plus-minus, and the higher number sort of indicates a player that has been on the pitch when the team has been doing well. And the lower value indicates a player that has been doing worse when the team has been doing worse when that player has been on the ice in this case. This idea of plus-minus spread through the NHL, and the official NHL page actually started publishing these plus-minus scores sometime in the 1960s, and they are still being published as of today on NHL.com. This was the early developments, and nothing much happened in terms of making this a more useful metric until sometime around the year 2000. At that point, Wayne Winston and Jeff Sagarin developed something that they called the WinVal, which is essentially what I refer to as an adjusted plus-minus. They sold their system to Dallas Mavericks, who used it at least for a good while. And it was kind of a secret. It was not until 2004 that anyone, as far as I know, wrote anything about it in public. And at that time, it was Dan Rosenbaum who wrote about this metric. So the first plus-minus is basically just a count metric, right? You just count what happens from the perspective of a player. So what was the novelty with adjusted plus-minus? Well, this was the first regression-based plus-minus rating. So the idea is then to use a linear regression model to isolate the contribution of the players, taking into account also the opposition and the teammates of a player. So essentially on the right-hand side here, we have the dependent variable. And the dependent variable is the observed goal difference in a certain segment of a match. And then on the left-hand side, we have the independent variables. And they are simply indicator variables, whether or not a given player was appearing for the home team, then the indicator variable is 1, or for the away team, in which the indicator is -1. And then the indicator is 0 if the player did not appear at all in this particular segment. And when estimating this model, the regression coefficients, the betas, represent the rating of a player. So if a player is associated with performing well, then his rating will be higher than the other players. There are some issues, though, with this regression model, and that is there's a lot of collinearity if you put up the matrix. So many of the players, for example, will tend to appear together, and many of the players will tend to appear only in a few matches or in a few segments. And therefore, when you just use ordinary least squares to estimate the model, there's a lot of noise, and the ratings become very erratic. And it took another 10 years roughly before someone proposed a solution to this. And this was published in a conference proceeding in the MIT Sloan Sports Analytics Conference by Joseph Sill. And his idea was basically to use regularization. So if we take a look at this from the mathematical point of view, at the top here, we have the adjusted plus-minus ratings. They are estimated simply using the method of ordinary least squares. So we simply minimize the square deviations between the left-hand side and the right-hand side, essentially in the regression model. But this regularization idea is not only do we want to minimize the square deviations, but we want also to add some kind of penalty on the regression coefficients, so as to basically prevent them from becoming very large or very small. So this means that we are introducing a bias. We tend to group ratings together around 0, but we reduce the variance in the estimates. So it leads to more stable ratings, and those are presumably better representatives of the true strength of a player. So given that, this was basically the situation when around 2015, so around 5 years ago, I started working in order to see if this concept could be applied to soccer. So before this, the adjusted regularized or the plus-minus ratings, which is what's still introduced, had been attempted both for basketball and NBA players and for ice hockey and the NHL by different authors. But nobody had really succeeded in doing this for soccer. And there's a number of reasons why even this regularized adjusted plus-minus rating is not really sufficient to derive good ratings for individual players in football or soccer. So what are some of the issues in soccer that are special there? Well, for one thing, there are very few goals. If you compare to basketball, there's 2 orders of magnitude difference in the number of goals in a game. There are also very few lineup changes during a match. And this is important because in these regularized plus-minus ratings, you tend to have one observation for every, let's say, stint of the game where the players on the pitch or on the ice or on the field do not change. So whenever you have a constant set of players on the pitch, that sort of gives you one observation. And in both ice hockey and basketball, you have a lot of more substitutions during the game than you have in soccer. As opposed to basketball, in soccer, sometimes there are missing players due to red cards or due to players being injured after all the allowed substitutions have been made. In ice hockey, people usually deal with that by estimating separately a plus-minus rating for shorthand situations and for full team situations. Also in soccer, at least in the European leagues, there are many divisions and many leagues that has some interaction, but it's relatively limited. So it's a different league structure compared to what you have in the American leagues of basketball and ice hockey. So to deal with these challenges, one way is to allow yourself to use multiple seasons in order to estimate ratings and to use multiple divisions. So you have more observations, you have more data in order to see if that can sort of overcome some of the issues. This has some effect on the interpretation of what you get. So whereas in NBA, for example, you can have presented plus-minus ratings that is for one season only, and it kind of makes sense to look at it. But for soccer, and at least what I have been able to work on so far, we are really estimating the career output of a player. We are not really looking at which player performed best in a given year, because even that is too noisy in this setting. So we are really looking at the adage that class is permanent and form is temporary. So we're really trying to find the class of a player. Using several seasons and using multiple divisions lead to some challenges that we need to resolve. For one, the abilities of players will change over time. So we need to deal with that. Players typically start very young and then they become better. They reach a peak age, and then maybe they start to decline physically after that. And we must also sort of address the issue of divisional differences. So a player appearing in the English Premier League is probably at a different level than someone appearing in the English League 2, for example. So we need to deal with these things. So in order to sort of allow more advanced versions of the plus-minus ratings, I'm going to step slightly away from the pure statistical regression models. I'm going to frame the problem basically as an unconstrained quadratic program. So now my background in optimization kind of shines through, and maybe I'm lacking a little bit of statistical rigor in what follows. Maybe I'm leaning a bit towards machine learning, but I hope you will excuse me, even though I do this. It's all trying to predict something in the end, right? So if we look at my expression here, I'm basically saying that this part here is hiding the dependent variable. So this is the observation. This is what we cannot basically change. This is what we observe. And then over here, which I refer to as the left-hand side, this will be my predictors. This will be my independent variables, how I try to explain what we have observed. And so we're basically still wanting to minimize the square deviation between these two. And then we have the regularization here, which I'm also going to adjust a little bit at the end, but now it's sort of encapsulated in some expressions here. So this is the model. This is what we are going to work with. We are also looking at a set of matches between two teams, each match. And each of these matches are divided into a set of segments, where, as I hinted before, basically the segments are starting and ending when you have substitutions or if you have red cards. And I sometimes use V here as a shorthand for the set of variables. Well, variables, because I think of this as a optimization model. You would probably talk about them as regression coefficients if you are still in your statistical model framework. All right, so now that we have this expression, we can try to talk about some extensions. The first extension that I want to mention is that more recent information is typically more valuable when you try to estimate how good a player is. So we introduce some weights for each observation. So denoted here by W and as a function of M and S. So basically a function of the segment that you are looking at. And so we basically weigh both the explanation and the observation equally. These weights are based on 3 different criteria. First of all, how long is it since the match was played? And we are exponentially downweighing all the results. So they become less and less important for the current day rating of a player. We also put a weight based on the duration of a segment. Presumably here we are thinking that shorter segments are somehow more noisy or less informative. So we have higher weights on longer segments because they kind of they are more representative of what is going on. And there's also a factor in this weight that is based on the goal difference at the start and at the end of the segment. Possibly based on the observation here that closer games, that is, there are fewer goals, are more random than more lopsided results, which is more clearly indicative of one team and thus one set of players being stronger than another. So to facilitate a few more extensions, I'm going to split the explanatory variables into different parts. So basically there are 3 parts. Some parts of the variables describe properties of the match itself. Some parts of the variables describe properties of the segment. So they are different from each segment within the match. And some parts of the explanatory variables are related to the players involved. So basically, we are adding up some properties of the players on the home team. We are subtracting some properties of the players on the away team. And then we are adding some properties from the segment and from the match. And my first example here will be related to the match. So with regards to the match, we have one type of variable, and that is to represent the home field advantage, which is typical in soccer and many other sports. The away team has to travel, the home team has the advantage of the crowd, and so on. And so we have one variable or one regression coefficient representing the home field advantage. If the match is not played on neutral ground. Of course, if the match is played on neutral ground, which happens in the big finals, for example, of the Champions League and so on, then the home field advantage disappears and is set to 0. Basically, in terms of estimating ratings, the home field advantage is not important at all. And that is presumably because most players tend to play as frequently on the road as they do at home. Nevertheless, we estimate separate home field advantages for different countries because it tends to vary a little bit between countries and also between different types of competitions. The third extension is to ensure that segments with missing players are dealt with properly. And there are 2 adjustments being made here. Let's start at the bottom. First of all, we are adding a separate variable here to represent the fact that one team has a missing player. So essentially, each team can have up to 4 missing players. If there are more than 4 missing players, then the match will be aborted by the referee. So this is the maximum. When players are missing, we also have to adjust for the contribution of each individual player. So what we're doing here is essentially we are dividing by the number of players present for the home team and multiplying by 11 just to scale things up, so that essentially these player contributions, they correspond to sort of the average contribution of a player in the match. Right. The fourth extension is about modeling the age effect. So what we have here is, I guess I will not explain this particular mathematical expression. At the end of the talk, I will give you a link, and on that link, you can download some academic papers, and they will go into more detail about the modeling here. But essentially, if we don't try to model some kind of age effect, then we are implicitly saying that the strength of a player is constant throughout the data set that we use for estimation. And since we are using many seasons of data to estimate, this is sort of obviously not true. So we are therefore trying to add some variables here to represent the fact that a player has sort of a baseline playing strength, and then its rating will vary over time. So we essentially have tried 3 different approaches here. We have tried to let this age effect be basically a quadratic function of the age. We tried a cubic function of the age. And what we used in the end is to say that the age effect is a piecewise linear function of the age. And when we estimate this, we get something similar to this. So here you can recognize the quadratic curve, the cubic curve, and then the piecewise linear curve, which we use in the end. We can see that this is plotted from ages of 16 to 42, which sort of covers most of the active players in typical top league football or soccer. And then we have sort of here how big the effect is. So we see that the peak age is by the model estimated to be around 26, 28 years old. And then there's a sort of an increase in the playing strength up to that point and a decrease afterwards. The piecewise linear function is estimated with basically 1 line segment for every year in the age domain here. And so we see that it's slightly noisy when estimated on this particular data set. It goes a little bit up and down. So that's the disadvantage of the piecewise linear function, that it looks a little bit noisy and unreal. But I think it handles better the effects at the end of the age scales. So when players are very old, they seem to decline faster than the quadratic and the cubic functions can allow. And when they are very young, they tend to increase quicker in playing strength than the quadratic and the cubic functions can express for us. All right, one more extension before we are able to sort of conclude this model and talk about it in general. When we have different leagues and different divisions, there's a problem with the regularized adjusted plus minus ratings. So what the regularization does is that it basically forces all the regression parameters towards 0. They are shrunk towards 0. So if you have a player that only appears a couple of times in your data set, the rating of that player will be close to 0 because of the regularization. However, that's not realistic, right? If you have one player that appears for a few matches in the English Premier League, and then you have another player that appears for a few matches in, let's say, the 4th level of the English system, it kind of makes sense that these players should not automatically be shrunk towards the same value, because there's such a huge difference in quality between the leagues where they appeared. So to compensate for this, we are replacing the regularization parameters for individual players by an expression that essentially pushes a player towards similar players. And similar players in this case are picked as the teammates of a player. So essentially for every player, we look at which are the players that have appeared together with this player for the most number of minutes. These are classified as the similar players to that player. And then we regress, or sort of the shrink, the rating of a player towards the ratings of the similar players. We are also at the same time adjusting this a little bit. So there's still a slight tendency towards pushing ratings towards 0, but it's a combination of pushing them towards 0 and pushing them towards similar players. And that's basically one of the models that we have attempted. So in the end, you have this large unconstrained quadratic program. And when I say large unconstrained quadratic program, and I illustrate it with this slide, I don't mean large because I have expressed it in a very roundabout way on this slide. I mean large in the sense that there are many observations and many variables. So there are many constraints, or many rows and many columns in the matrix here that we try to solve. So essentially, if you have a data set, a typical data set, if you take the top 5 leagues in Europe and you estimate ratings for, let's say, 5 to 10 seasons, somewhere between there, you very quickly get in the range of 10, 20,000 matches. And each match is on average split into 6 or 7 segments. So we suddenly have like 100,000 easily segments, and that would be 100,000 rows in the model. And we would typically have several tens of thousands of players, each having their own variable in the model that needs to be estimated. So by large, I simply mean that there is much data here. So to estimate this model, basically to solve it, I realized that this is essentially a convex program. So we can solve it by simply using a gradient search that will converge to the optimal solution, which will give us the best estimates in this case. All right, so this is the model. And I guess the next question is, are the results of this model, are they sensible? Do the ratings that we get out of it reasonable? So I have some slides here. They are slightly outdated. They were created before the Corona outbreak. So January, February, basically this year. And these can be used sort of as a phase validity, right? So they can basically, we can ask, these are the ratings. Do they make sense based on what we sort of know from subjective opinions on these players? So I have a rather big database at this point with 18,400 players that have appeared in at least one match during the last year. And these are sort of the top players according to the model. So let's say this column is the number of minutes played in the database used to estimate the ratings. And the rightmost column there is the rating, the current rating estimate. And the column in between here is what I would like to refer to as the peak rating. So essentially, if you take into account that each player follows this aging curve, they are at some point now in this aging curve, and if you sort of move them towards the peak, this is how high that peak would be for that particular player. So the best players in the world according to plus minus rating at this point would be this list. We can also plot graphs like this, where we show the development of the plus-minus ratings over time. This graph is being created by basically recalculating the plus-minus ratings up to every given point in time. So basically, we are re-estimating the model for this graph once per month. So every 30 days, the model is re-estimated using up-to-date data. And then we get these curves. These are showing Neymar, which is an up-and-coming player. Messi, which has been regarded as one of the best players for a long time. And Thomas Müller, which is a very stable performing player in Bayern Munich and Germany. It is also possible, as another way of doing phase validity, to look at the average ratings of the teams. So if we take the ratings of, let's say, the 15 best players on every team and take the average, then we can rank each of the teams together as well. And again, I find that this rating list pretty much is in line with what other types of rating methods and also experts would do in order to rank the different teams. So this would be the best 10 teams in around February 2020 out of 760 different teams in the database. So it picks out the best teams and put them in some kind of ranking there. And again, you can look at the development of the ratings of the teams over time by looking at the best 15 players across different years.
Lars, a quick question.
Yep.
Given that the target variable is goals across the segment, I mean, is there a way of interpreting the ratings themselves in terms of the sort of the goals added or the contribution of that individual player, the average contribution in a given match?
Yeah, so essentially if you have two players and if you look at the difference, then it would be in a sense similar to the change in the goal difference if you substituted that player for the other per 90 minutes. So they are scaled, these values, to sort of correspond to that. This means that the ratings get sort of, if we go back to the player list here, the ratings get sort of inconvenient values. They are not very easy to sell to the general broad audience, but they do have this meaning that if you substituted Neymar for Thomas Müller, you would lose 0.007 goals per 90 minutes on average, if you were to trust the ratings.
Thanks.
Yep. So finally, we can do the same on the league level as well. So we had the player level, we had the team level, and now we can aggregate sort of all the players in a given league. And here I've done that for the previous season. And that gives us sort of a ranking of the leagues as well. It can sort of say something about the difference in quality between leagues. So you may be interested in finding here that the Major League Soccer is number 8 on my list. Fairly similar rating to the championship level in the English system. And comparable to the Russian Premier League or to the Portuguese Primeira Liga, according to the model. Of course, MLS is a little bit special because it doesn't have too much interaction with the other leagues. So it's probably more uncertain exactly where it is in this hierarchy. Whereas for the European leagues, they interact quite a lot through these European Cup competitions like the Champions League and the Europa League. But there is some interaction with players moving from leagues to other leagues, and in terms of national teams having matches together. I would like to say a little bit about how these ratings are evaluated, because what we presented here was just sort of lists, and we can use subjective opinion to see if they match our expectations or not. So essentially, when developing this method and when tuning hyperparameters and so on, I have used 2 criteria, which I refer to as a representation of validity and reliability. So I think I will jump into the explanation first and then maybe go back to this slide. So the first axis on the previous diagram referred to reliability of ratings. And this is basically calculated using something I think is known sort of as a split half reliability. So you have a big data set. You split the data set into 2 halves by random. and then you calculate ratings for each half independently. That gives you two different rating lists, but containing an overlapping set of players, because some players then are present in both of these halves of the data set. And what we do then is to basically calculate the correlation between these two rating lists. So we use Pearson's correlation coefficient, and that gives us a measure of how erratic are the ratings, right? Can you take sort of a different data set and get the same rating list? And if I go back now, our final method is the one here to the top right, and it basically gets a correlation coefficient of about 0.9 something, depending on how much data you have and so on, but around 0.95 or between 90 and 95. So the other versions here in the middle are sort of other versions of the plus-minus rating system that we were testing. And down here at the bottom left, we have the sort of the pure plus-minus that essentially encapsulates what NHL has been doing since the 60s. But again, these are all different versions of plus-minus, so it's only a relative ranking between them in that sense. And the second axis is an attempt at capturing the validity of the ratings. So do we measure what we hope to measure? And I have said that what we want to measure is basically our ability to predict future outcomes of matches. So if you can give me the starting lineups of a given match, I should be able to tell you what is the likely outcome of that match. So the procedure here is that we start with some data, past matches, that we simply use to produce ratings. So we use a lot of observations, or a lot of matches, just to be able to calculate ratings. Once we have enough data to calculate ratings, we start looking at matches where we look at the average rating of the home team minus the average rating of the away team. That is our predictor in this case. And then we observe what is the outcome of the match. And then we create lots of those observations, and then we put them into some kind of statistical model that we will use to predict future outcomes. So in our particular case, we have most frequently used an ordered logit regression model because it sort of fits with trying to predict a home win, an away win, or a draw. So there are three ordered outcomes. So the dependent variable is sort of ordered. And it has worked well for us earlier as well. And then you start to observe future matches, and then you can use the prediction model to create probabilities for home win, away win, and a draw. And then you compare that with the actual outcome and calculate a loss function. So we most typically use the quadratic loss function, and then we get these sort of loss values that you see on the x-axis here, on the first axis. Again, it maybe doesn't say too much unless you have a benchmark. So a typical benchmark would be betting odds. So using the betting market to say this is more or less the true probabilities, and then we see how close we are to those. They are not indicated on this graph, but I guess for this particular case, the betting line with the betting market would probably be around where my pointer is now. So it would still be quite a bit better than just using the plus-minus ratings. But we have been able to close the gap quite a lot from the very naive methods. Right. Next, I would like to discuss, I guess I have some more minutes. Maybe Mark or someone can give me sort of an indication of how many minutes I have left. Because I can talk about this for many, many hours, so you have to stop me at some point. So together with Gary, we did some work where we basically wanted to see, okay, we have these top-down ratings, the plus-minus ratings, that don't care about what the players are doing. But we also had a data set where we had event data, so we could look at what the players were actually doing. So what we did was essentially to look at different performance indicators of players and see, well, we did two things. So this slide essentially shows can we explain the plus-minus rating of a player through these observed performance indicators? And the answer is that out of the variation we have in the plus-minus ratings, we can roughly explain about 36% of that. So this table shows sort of the relative values of the different performance indicators. How much do they explain of the variation in plus-minus ratings? And these are scaled, so they add up to 100%. So they show basically which are the important performance indicators. And there's kind of an interesting aspect to this, and that is they kind of make sense. So for goalkeepers, for example, saves are important, passes play a role in terms of passes completed, and sort of the offensive metrics, they don't matter. But if you look at an offensive player, so this is a forward, then the important things are goals scored and key passes and shots on target and things like you would expect to matter for an attacking player. So this is also kind of a validation of the fact that the plus-minus rating is related to the correct types of events. We also did one more test with these performance indicators, and that was to try to use them to improve the predictive ability of the plus-minus. So basically, can we add some of these performance indicators to a prediction model together with the plus-minus rating in order to make better predictions? And the answer is that most of these are useless when taken together with the plus-minus rating in terms of prediction. There were only 2 of them that actually had any positive effect, and that positive effect was not very big. Another study that I did was with another colleague here. And the idea here was that one criticism that I have seen against plus-minus ratings, in particular for soccer, is that they are merely picking up the quality of the team, right? They are not able to distinguish the players. The players are just randomly distributed through the average of the team. And so you're essentially doing nothing else but capturing the team strength. So to test that hypothesis, we wanted to have a team rating and then add both the team rating and the player rating when trying to predict future matches. And I'm sorry to mark, we didn't choose the Glicko, we choose the ELO, but it's easier, right? It's easier to implement. So we used that, and we used 2 different types of prediction models. My good old friend, the ordered logit regression model. And then we also built basically a competing risk model, which is an interesting thing here. And then we measured the performance of these using different sets of covariates and using 2 different types of loss functions. So we have the quadratic loss function, as we used before, but also the informational loss function here. And okay, so the statistical relevance is not pointed out here, but what we found is that if we take the ELO ratings and use those for predictions, and if we add the plus-minus rating as well, then we get predictions that are statistically different from only using ELO. So they are better, and we used a paired t-test to establish that they are statistically better. We can see how much different they are. They are not hugely different, the loss values here, but they are statistically different. So at least we are picking up something that a pure team rating like the ELO ratings is not picking up. Right, so that basically concludes the main bulk of my presentation. And then I have a few more slides with some bits and pieces. And one thing I wanted to mention is that we used linear regression models as a basis for our plus-minus ratings, but there are alternatives, and other people have tried different things. So in some unpublished work, Villain and Kolkovsky, for example, used an ordered probit regression model, where the dependent variable is the number of goals scored, same or similar to what we have, and the independent variables are split into offensive and defensive ratings. So essentially, in the model that I presented now, the dependent variable is the goal difference, and we only have one independent variable for each player. So they have then 2 independent variables for each player, corresponding to offensive and defensive ratings. And the dependent variable is not the difference, but it's basically the observed number of goals by one particular focal team. So they get twice as many observations per segment as we do. In ice hockey, even other types of models have been attempted. So Thomas and others, for example, used hazard functions to model the goal scoring processes, and then with covariates for the player ratings in that setting. Myself, I have recently tried out to splitting the ratings into offensive and defensive ratings, similar to Villain and Kolkovsky, with the dependent variable being then the number of goals scored by each team. And this worked more or less in the same way as my previous models, so without splitting. It's basically not able to predict any better. But it gave some insights. I think it's worthwhile to point out that there is, of course, some uncertainty here. So when we create the player rating, we might like to ask, what is the uncertainty around this rating? And since my model turned out to be not particularly fitting towards the existing statistical models, I chose to use bootstrapping to evaluate the uncertainty. That is to evaluate uncertainty due to the data, at least. There's probably some uncertainty due to the modeling decisions, but that's not captured here. Here I've illustrated that not in terms of player ratings, but in terms of the age curve. So in my model where I had offensive ratings and defensive ratings, these are sort of the estimated effects on the defensive rating of a player and on the offensive rating of a player for one particular data set, based on or depending on the age of the players. So it's interesting here to see, for example, that these bands here correspond to sort of 95% confidence intervals based on the bootstrap. And they are quite wide in the areas where you have few observations. So very old players, very young players, and they are more narrow where you have more information. So you have more observations around the peak age players. So the conclusion here, for example, could be that if you have a young player, they are more likely to hurt your defensive performance than the offensive. So the age curve here is more flat in terms of the offensive contribution than it is for the defensive contribution. So that's kind of the insight you can maybe gain from a model where you split into offensive and defensive ratings. One more slide. I just wanted to illustrate this because I like it a little bit. This competing risk model, where we basically estimate scoring rates for the teams as a function of several covariates, including the red cards, the ratings of the players, and things like that, allows us to simulate a match from a given point in time. And so we basically can have these real time estimates of the winning probabilities. So we can then, the blue area here is basically corresponding to the probability of a home win, in this particular case with Carlisle against Bury. And the pink here is an away win, and then the gray is a draw. And then we can see how the different events, like the goals scored here is the footballs, yellow card here, there's a red card, and these are substitutions, how these events influenced the winning probabilities. And then I will just wrap up by saying that there is more information out there on plus-minus ratings. So I have this pointer to this web page, and on that web page you can find further pointers to some academic papers written on the topic, as well as some other presentations that are available on YouTube, which sort of goes through my process of developing these ratings. So I guess I should thank you for listening, and then I will let Laurie take the floor again.
Thanks very much, Lars, for a great talk. Perhaps we can all take a second to thank Lars in whatever way feels most natural to you. Okay, so we have about, let me see, we have 8 minutes for questions before the end of the hour. So if you could raise your hand on the participant screen, or just jump in if no one else is already talking, then you can go ahead and sort of pose your question that way. So Andrew, do you want to go first?
Hi, Lars. Really great talk. One question I had: when you have the age curve,
Yep.
was that kind of the same age curve for everybody, or did you like a position dependent age curves?
That's a good question. And the answer is that it was the same age curve for all. I did try to model it separately for different types of players based on their position, but it did not really give a good effect in terms of the predictive outcome of the ratings. So it could be that it could be that at the time I didn't have a large enough data set. You need more data in order to separately have an age curve for, let's say, defenders or for attackers. But right as of now, it's the same for all the players.
Yeah, because the kind of the general thought process is that the for defenders and goalkeepers the kind of peak is a lot later than attacking players, for example.
Yep, there have been some papers written on that where people sort of study the aging curve based on sort of indirectly through ratings calculated based on the bottom-up approach, and they would then find that it differs slightly from defenders and goalkeepers and forwards. Perhaps the difference is not as big as we would like to think, though.
I see. Cool.
So I will now call on Andrew Popolo to ask his question.
Hi. So I guess my question is kind of two parts, kind of related to each other. The first is, did you take national team results into account to kind of get some more cross-pollination?
Yeah, so in the biggest data set so when I presented these rating lists, there I have the national teams involved. In some of the particular academic studies, and so some of the results presented later, there was only domestic leagues present.
Okay, and I guess the second part of my question is, did you look into how player ratings changed as players transferred from teams that were of different qualities?
That's an interesting point. I have noticed that frequently a player will, the rating of a player will change when moving, let's say, to a better team. It tends to kind of follow. So there is definitely an effect of this in there, but I haven't really analyzed it properly. So I can't really say how big it is or whether it's definitely there, but I sort of have seen examples of it in the data.
Thank you.
Dwight Wynn, next question.
Hi, I also had a question about the age curve.
Yep.
So my understanding is that piecewise linear is essentially estimated at every difference in age. Have you considered using a 3 or 4 knot spline to account for what you think is happening qualitatively?
Yeah, that's probably a very good comment. I haven't thought about it. I'm not sure if it fits with my current, let's say, estimation framework, but it could be that it does. I have to say I'm a little bit ignorant about that particular way of
because that would get
framework.
rid of some of the noise.
Yeah. So what I'm doing is that I'm using the regularization trick. So I'm essentially, again, not necessarily regularizing towards 0. So I'm not shrinking towards 0, but I'm shrinking towards the average of the previous and the next value in the chain of ages. But probably from a modeling perspective, your suggestion is much better.
Thank you.
So the next, we've got a few people who want to ask questions from the chat as well, but I'll ask Rick Cleary to ask his question first.
Yeah, thank you. Thanks for a great talk. You had another age curve right near the end of sort of value by players, was just 2 or 3 before. Yes, that one. So I'm really interested that both seem to take a little jump back up near 40. And I wonder if that's just a small sample size effect. I know hockey a lot better than I know soccer, but the players who can survive till 40 tend to be the real superstars. So I was just curious if that's, and it also makes me wonder if there might be some sort of contract effect. Players who have multi-year contracts, they often run out in the late 30s, and then only a few are good enough to extend. Anyway, I was curious about that, and clearly it looks like, well, not so much on the offensive one. And the defensive one, it looks like it may be a sample size thing because the variance seems to jump up at the end too. So I'm curious if that's what you think about that effect.
I think it's a combination. I think it's both the survival bias, and I think it's the estimation itself because of the few observations. I still think I'm drawing it towards 0 in some way. So there's a combination of the way it's estimated here, and I mean the fact that, as you say, it's the same in soccer. The players that will stay active in the data that I cover in my database will be those superstars that have better longevity than the other players.
Yeah, it seems like a neat potential student project to look for that effect across different sports. So thank you.
Yeah.
Great. Ryan McShane, you said you had a question.
Yes. So following up, I forgot who asked it, but following up on the international play question, how does, let's say, the World Cup, did you look at the World Cup, how it rates among all the leagues? Is World Cup play at a higher level than the Premier League, lower level? Did you look at that?
Oh, that's a good question, and I guess I should have prepared something on that. I think if you look at the World Cup as a totality, then the average is not as high as, let's say, the end play of the Champions League, because you have some nations qualifying that are not as good as sort of the best club teams. I mean, it's a typical question, right? Is the best national team better than the best club team? And the truthful answer is that I haven't really checked on that. I would guess it's fairly similar, right? It's that's my guess. But maybe the club teams are even better these days. I can look into it later, and if you send me an email, I can check it.
And I think, okay, so Mark Glickman has a question.
It was a really nice talk, Lars. Really clear, very very nice, nicely done. I actually had a question about your opinion of a slightly different approach to regularized adjusted plus minus, which would take advantage of working with more detailed data if it were available on player positions. It seems like there's a kind of a class of work that has to do with assigning things like win probabilities or basic strategic advantage to the placement of all the players, players on the pitch and the position of the ball, and that you can assign essentially individual values to to particular situations, and so use that as a proxy for a scoring outcome. So if a team is able to achieve a certain situation or a certain position, instead of just working with goals scored, use that very detailed information as the response variable for these regularized adjusted plus minus approaches. You have any thoughts about that, or are you aware of work in that area?
Yeah, I'm doing some at the moment.
You are. Okay.
Basically on this, if you're familiar with something called VAP, I guess it is called something in soccer. Maybe Laurie knows more about this than I do. But my idea there is basically to add up all these bottom-up rating for a segment, right? And use that as the dependent variable. I haven't found a better way to do it. And I have some interesting results. Essentially, it doesn't seem to give much because it's strongly correlated with the goals in the segment. Essentially, these these bottom-up ratings tend to be kind of a zero-sum game. So you do some positive things, but then you lose the ball, and then that cancels out whatever you did that was good, unless you score. But then it's a +1 again in the bottom-up rating as well.
Okay, I guess I was thinking that it would be kind of like two separate analyses stacked one on top of the other. One would be just a purely player free, where you don't keep track of player identities, just do something based on positioning of players. Do that as one pass so that you have essentially a mapping of where players are in the pitch to some score. Mm-hmm. And then as a completely separate analysis, do something like regularized, adjusted, plus minus using those outcomes, as opposed to blending them together. I guess I was thinking. But anyway,
maybe there are some details I'm missing, but I think I'm doing something similar to what you are referring to.
Okay.
Well, we're a few minutes past the hour, so I think we'll finish the seminar there. Let's just quickly thank Lars again. And Mark, when is the next?
So in 2 weeks. Yeah, next one is going to be in 2 weeks from now. And so just pay attention to your emails. All the details, as usual, will be sent through the usual means that we send emails out. So hope to see you all in 2 weeks then.
Let me also thank everyone that asked questions. I really liked responding to those, and thank to everyone for listening. And just get in touch if you have any more detailed questions.
Thanks everyone for calling in.